Open and remote access sensing is basically a mean to share the utilization of in-orbit resources of a small CubeSat among several users with autonomous and potentially isolated ground stations. I will discuss this in the following slide, how it is achieved and what is the particular objective of the Oras project. This concept and this presentation was basically developed as a joint effort of professors and students of the Satellite Instrumentation Master, which is held at the Gulit Institute at the Argentine Space Agency, or CONAE, which is located in Cordoba, Argentina. So, to take a look at the Oras motivation, we propose a first quick study, and this is just two typical components or subsystems that one can commercially acquire from. This is a particular vendor, very popular vendor for CubeSat, which is called GomSpace. And if we take a look on the left, we see that we're talking about what can be seen as an onboard computer, which actually is also used as a transponder unit. But I want to focus on the properties of this component, and we see that this is not an expensive subsystem. This is a very small subsystem and also very power efficient, targeted for CubeSat. This is very small. This type of subsystems are really showing quite remarkable processing performance and storage performance, at least in comparison with what we see in traditional space components, which are not CubeSat based, but are based like for general and more reliable space missions, to say it somehow. This particular component is talking about a dual ARM Cortex processor with clocking at 800 megahertz, which is quite a powerful processor, and it's already including 1 gigabyte of RAM and 32 gigabyte of non-volatile storage, and this can easily grow to maybe a few hundred gigabytes with barely no effort and also no very small cost for a traditional CubeSat mission. But this remarkable increase in performance in terms of storage and processing is unfortunately not seen in communications equipment. And let's go to the subsystem on the right. We are talking about Magnum.com, which is also a very popular CubeSat subsystem working on the UHF and VHF band, and we can see that the data rates of the systems are ranging in a few kilobits per second to a few hundred kilobits per second of data rate. This does not mean that the technology is not up to the challenge of going higher than this, but this means that actually the channel characteristics of such CubeSats are really narrowed in terms of available throughput, and the equipment has to basically keep up the data rate that can be accommodated in these type of channels. And if we make a very quick calculations such as the one we show below, with this type of data rate in an average 10-minute window of communication or of a pass of a satellite over a given ground station, we can see that only a few megabytes can be downloaded, and even in higher data rates, talking about 1 megabits per second and so on, we are still not using barely 1% of the storage capacity that is offered by the product here on the left, which are talking about the Nanomind Z7000 from GomSpace. So this is a particular study and a particular analysis, but in general this applies to most CubeSat subsystem available, commercially available nowadays. So in general, the Oras motivation is that the state-of-the-art technology for spacecraft, or small spacecraft, tend to provide the following features. We're talking about very large storage in terms of capacity and data storage volume. We're also talking about significant processing capabilities, such as this type of processors, which are also interestingly very similar to what the processing we are seeing in our most smartphones nowadays, which is actually the same principle basically being put in orbit in the CubeSat missions. But what we are not seeing is that a corresponding increase in the data rate for downlink these large volumes of data from space. And again, this is constrained by available in-orbit power and limited antenna gains that basically limits the channel throughput that can be obtained from a given CubeSat. And this has not necessarily has anything to do with the RF technology or the communication protocol limitations, but are really physical limitations typically seen in the CubeSat. As a consequence, what we have is a downlink communication channel, which quickly becomes a bottleneck in any type of satellite architecture. So the objective of Oras is to widen the downlink bottleneck by doing the following: allowing several ground stations equipped with standard communication hardware, which is like publicly available in the market and can be accessed by any customer around the world. And by using this such a standard communications, anyone around the world can access, command, manage, and download instrument acquisition from the CubeSat. As crazy as this sounds, this can still be is a very interesting way of tackling the problem of the downlink bottleneck, because what we are basically doing is just widening the time access for satellite, and therefore optimizing and increasing the downlink the data downlink that we can get in such a low throughput channels that we were discussing. So this is somehow analogous to making and to creating a very large distributed ground station all around the world. Again, another thing that's also behind Oras is that any acquisition that can be commanded by anyone, they might be previewed by using thumbnails, like smaller resolution version of the acquisition, but not necessarily downloaded in the end, so that users can here on ground select which of their acquisitions are going to be finally downloaded instead of just downloading the full resolution version directly, and therefore saving significant amount of the channel resources. But obviously, such an approach has several challenges to be met. They are not few, and they are not easy to tackle, and is the basic discussion presented in these slides. So, Oras requires of non-trivial but highly developed protocols that enables three aspects. One of them is secure access. If we are saying that anyone around the world can just buy a material, can just buy a simple ground station equipment and access this satellite, we need to provide a secure access to authorized and authenticated users to command specific tasks and carefully choose functions to the platform. We are going to discuss in the following slides what we are proposing to tackle this problem, and another aspect of this first point is also accounting. I mean, if users are going to access the satellites, then it's not only a matter of being able to command and control such a satellite, but also being able to be restricted to make an utilization of a restricted utilization of a second point is the resource management. So we have a set of resources on board. We're talking about payloads, in this case, for instance, observation payloads. We're talking about memories. We're talking about processors and so on. So the correct utilization of these resources is crucial in order to avoid the users making like a malicious utilization of such resources, or to, let's say, overbook memories or overbook power or so on, in order to guarantee that the satellite can still be operating while being shared among different users. An interesting point also in this point, in point number 2, which actually drive us to point number 3, is that these users might not be necessarily connected. I mean, the satellite might not be necessarily connected to the main ground station while being commanded by these users. So this means that the satellite has to be quite smart in managing these resources, and this is actually drive us to point number 3, which is onboard scheduling. Which basically says, since the mission control cannot be continuously in contact with the CubeSat, all functionalities, particularly in scheduling decisions, has to be performed autonomously by the CubeSat. This means that if a user is asking me to take a picture of a given region of the world in such a way that the storage I would need to use to store such acquisition is not available at that time, the satellite has to be smart and autonomous enough in order to deny such a command for the user commanding the satellite at that moment. And this has to be done, again, without intervention from the main ground station, the main mission control. So let me quickly go over what is the Volcano project, which is a particular mission being developed by the master students nowadays, which basically tries to implement the Oras philosophy. And the Volcano project is a project focused on observing volcanic activities via a thermic camera, which is commercial of the shared industrial camera, which is going to be mounted in a LEO CubeSat, flying at around 600 kilometers, 98 degrees of inclination, and with a 6-month lifetime. This is as a Bobby 640 thermic camera. It's an industry available camera with a 640 by 480 pixels, which give this 80 kilometers and 115 kilometers cross-track swath of observation. And from the particular space agency in Argentina, they're interested in observing, obviously, the volcanic activities in the Argentinian mountains. But the satellite is going to be available and flying also all around the world. So this is quite interesting to see that such payload can also be shared and used among other observation users around the world from other countries. So I don't want to go into the details just to meet the time frame, but student has made already different communication architecture studies about the data rates and about what's the payload generation rate and so on. And this type of study not only applies to the particular case of the CONAE, the space agency using the observation from the local mountains, but also from other users around the world making commands to observe a given image and downloading them at their own ground stations without intervention for the Argentine Space Agency, except for the authorization and authentication of the users. Again, I repeat this point, which is very important. But we have all, in this particular Volcano project, we have all this communication architecture already selected and studied. Also, I don't want to go into details because of time, but we also have like different reliable architectures, how this camera is interfaced with, also different SMEA and FMECA, different foul mode studies and so on, as well as a different set of component selection, which is, there's really nothing new on this. This is a traditional satellite design process. What is interesting to see is that this is basically a particular mission, which is designed and in a traditional CubeSat way, but the philosophy of using the onboard resources is shared and basically is based on this Oras philosophy we just discussed. So in this context, the main challenges is software development. This is a space terrestrial interactive software that has to work from a ground perspective in terms of secure access and determining resource management rules, and that actually feeds onboard scheduling algorithms that has to be met without intervention from the ground station. So this is like a very complex space integrated software framework that has to be developed for the Volcano project and eventually for any type of Aura missions that we'll find in the future. We are actually discussing on how this approach can be made open source in the future, on what are the rules, what are the challenges, what is the best way of doing this. This is a discussion which is being held at the moment, because this is not a Volcano project dependent software, but can be a general software for other type of observation or even communication mission around the world. So to close, well, we introduced Oras as a means of enabling shared access of resources in order to overcome the bottleneck in the downlink channel. We discussed the 3 key enabling technologies: secure access, resource management, and onboard scheduling. We also discussed a particular mission that can implement this Aura philosophy, and we highlighted the main challenge as being the software development of this space terrestrial integrated software framework that needs to implement this type of features in order to become Oras enabled. And this is being held, as I mentioned, by master students of recognized master's space in instrumentation. And most of master student final works are actually focusing on this philosophy. And so we really expect the Volcano project to fly in the near future. So I thank you for your time, and I leave you here my email to reach me.